I'm very excited to introduce this topic of motion. Everything in the universe is in motion. So let's take a look at it. We will be dealing with a very specific example of motion, objects which are in constant acceleration or experiencing a constant acceleration. This is dictated by a few fundamental equations, which I will go through in a minute. But you basically have the theory on this worksheet. I've cut away all the fat, and you've got just exactly what you need here, nothing more, nothing less, to answer these exam style questions. I've then extracted all of the past paper questions for motion or kinematic equations, kinematics they call it, here from as far back as 2015. So you have a bunch of questions here. I've extracted them all and I've written answers for all of them. It's a pretty big worksheet. You've got all of my written answers here for you, and those will be in the link in the description, so you can download that and go through them and get an idea for how they like to ask on kinematics in your actual exam. Okay, so let's go through some theory. As I stated before, everything in the universe is in motion. It's a very interesting phenomenon and something actually extremely peculiar. You start to really think about it. Everything is moving. So we want to take a look at this, and physics is a pursuit of truth and understanding what is. So motion is a big factor in that exploration. So let's talk about kinematics. So we're dealing with the equations of motion for a constant acceleration. We have two things to start off with here, velocity and acceleration. So velocity is the change in displacement divided by time, and acceleration is the change in velocity divided by time. Displacement is simply distance in a specific direction. So if you were moving in a line, let's say, you could move 1 meter to the right and then 1 meter back to the left. Your overall change in displacement would be 0, because overall you haven't actually changed, because you moved 1 meter displacement wise positive and 1 meter displacement wise negative. So overall you haven't moved, but your distance would be 2 meters. You've moved 1 meter, 1 meter. We'll go into more of that later. Here you have, I've derived these kinematic equations for you. You can run through this. I'll quickly explain these. So basically the first equation, and these are actually all will be given to you in your exam as well. They're here. But these equations on motions are as follows. So if you have an object which has a constant acceleration, well, by just rearranging this first equation where v and u are its final and initial velocities, you can rearrange this to get this first equation, which is the final velocity equals the initial velocity plus acceleration times time. That's one equation we can use for objects in constant acceleration. The next two we find from a VT graph. Basically, the area under a VT graph. So this would be an object in constant acceleration. It moves from u, initial velocity, to v, final velocity, in a certain amount of time. The area under this graph is the displacement of that object. From that, we calculate the area and we get this equation here. We then substitute this equation into this equation. So we substitute these two equations into each other. The v equals u plus at, and the s equals half v plus u times t. And both of these equations are from this graph, in fact, because acceleration is the gradient of this graph and displacement is the area under this graph. We substitute these two into each other and we can derive these two equations here, which are very useful depending on the variables we're given in the question. We can use these equations accordingly. I have the actual derivations here. You can go through that if you'd like. I think it's important to know where these things come from, but they do give it to you. But that's where they come from a simple VT graph. A few note here is that, well, I've got all of these things here. S is displacement, U initial velocity, V final velocity, A acceleration, T time. You're going to need to know simple trigonometry. So basically, the velocity as a vector, right? Because velocity is just a vector, speed in a direction. Well, the vertical, it is made up of a vertical and horizontal component, and those can be calculated through simple trigonometry. So, you know, the vertical component will be v sine theta, and the horizontal component will be v cos theta. Find the angle, you can find it by this, and if you want to find the magnitudes, where you can find it through Pythagoras' theorem. That's basically all you need to know, and we'll reinforce this when we do questions. And finally, we will go into more detail on energy, but they love to mix in energy here to make, basically you make kinetic energy and gravitational potential energy calculations occasionally. So I just chucked it in here, but basically, you know, kinetic energy is just the energy possessed by an object in motion. If you have an object in motion, well, it has a kinetic energy, and that kinetic energy is equal to half mv squared, where v is the velocity. And the gravitational potential energy, this is simply the energy possessed by an object due to its position in a gravitational field, and that's equal to mgh. And these are actually very important energy equations, because, you know, all objects are moving and are at some position in some gravitational field. And so these two are fundamental to energy calculations. That's all the theory you need. The things I've boxed up are the most important things and the things that you should understand. I will reinforce this now by doing questions. Define the following displacement. Well, as I said before, displacement is just distance in a direction. And acceleration, from our definition, is just the change in velocity divided by the time taken to change that velocity. So in these kinematics, they're going to give you a lot of different scenarios. Basically, the scenarios will be, a lot of the time, it will be projectile motion. So we'll get a good understand that. That's just motion in a gravitational field. We have the arcing, it could be up, or it could be, you know, projected at some angle. So some car moves up a ramp as illustrated. The car leaves the ramp with a velocity of this at an angle. The horizontal component of the car's velocity as it leaves the ramp is 4.6 meters per second. So its velocity here is 5.5 meters per second. But this velocity is made up of a vertical and horizontal component, Vy and Vx, this being the vertical and this being the horizontal. And it says that the horizontal component, this Vx here, is equal to 4.6 per second. Okay, they're at a distance d apart and air resistance is negligible. Show that the car leaves the ramp with a vertical component of its velocity of 3 meters per second. Well, you can just find this through trigonometry, because v squared equals vx squared plus vy squared. So therefore, the vertical component of our velocity of this car will be vy squared equals to v squared minus vx squared. That gives us 5.5 squared minus 4.6 squared. 5.5 squared minus 4.6 squared. This is 9.09. So therefore, the square root of this will give us square root of this, get 3.014 dot dot dot, but rounded to two significant figures, which as I was looking through the answers, they always round to two significant figures. So just round to two significant figures. So rounded, so we Vy equals 3.0 meters per second, which is what they wanted. That's the vertical component of our velocity. Determine the time taken for the car to travel between the ramps. Okay, so with these kind of things, you need to write down what they give you. So, you know, we know the velocity, we know the vertical and horizontal component. We know that this thing is going to be accelerating at minus 9.81 meters per second squared, right? It's in a gravitational field, so it's going to have acceleration due to gravity acting down, right, in the vertical direction. So if we want to determine the time taken for the car to travel between the ramps, well, we could find the time taken to get to the center, because at the center, its vertical component of its velocity will be 0, right? It's moving up. As it's moving up, its vertical component of its velocity will be decreasing as time progresses, because it has an acceleration acting on it vertically down due to gravity. So at the top here, the vertical component of our velocity is 0 meters per second, because it's no longer moving up, it's only moving horizontally. So our initial vertical component of our velocity as it leaves the ramp is equal to, as we found here before, is this, u meaning initial velocity, so it's 3.0 meters per second. And our final will be 0 meters per second at the top of its flight. We have the acceleration due to gravity is minus 9.81 meters per second squared. So therefore, from acceleration equals change in v over t. Change in v is v minus u. So therefore t will equal to v minus u over a, rearranging for t. So therefore t will equal to v final at the top is 0 minus 3 divided by minus 9.81. That gives us minus 3 divided by minus 9. I kept it in this exact form on my calculator, but I got 0.307 seconds. Right? But that's to the middle. That means that the time taken to the middle is here, but the time taken will then be the same from here to here as here to here, right? The same acceleration is acting upon it. Nothing is changing between these two sections. So 2 times that, so the total time taken will be 2 times 0.307. So times by 2 gives us to 2 significant figures is 0.61 seconds. 0.61. That's your answer. Calculate the horizontal distance d. Well, we have the time taken, 0.61 seconds. We have the horizontal velocity, Vx, which was 4.6. And because throughout the entire flight, the horizontal velocity will not change. It's not being affected. It's not deaccelerating. Nothing is causing it to deaccelerate. The only deacceleration that's happening is in the vertical direction, hence the arc. So this is consistent throughout the entire motion of this car. So that means, as velocity equals distance over time, is that distance will equal to vt. We have a velocity and we have a time. So our distance across this these two ramps, will just be 4.6 times 0.61. 4.6 times 0.61. It's 2.8. So to 2 significant figures is 2.8. This is 2.8 meters. They write it for us. I really feel like they don't give you enough space in these things. Okay, so calculate the ratio of the kinetic energy of the car at its maximum height to the kinetic energy of the car when it leaves the ramp. Well, the kinetic energy of the car, like I said before, at its maximum height here, well, that means that all of its velocity is acting in the horizontal direction. So, and I said before why, but the horizontal component of the velocity will stay constant, will stay the same throughout this arc. So its velocity at the top is going to be all of this vertical horizontal component. So it'll be 4.6. So kinetic energy at the max height, well, this is just going to be equal to EK is going to be a half the mass times this, Vx. It's 4.6 meters per second. And the kinetic energy when it leaves the ramp, so when it leaves, this is just going to be equal to a half m times v squared, because that is the velocity when it leaves the ramp, is this. right? And this is the velocity when it's at the top, because all of this velocity is that vertical horizontal component. Well, they don't give us the mass, but when you find the ratio, these two, so the ratio will equal to this divided by this. Well, that's going to cancel with that, and you're just going to get Vx squared over V squared. Therefore, the ratio will equal to, well, what is Vx? 4.6 squared divided by velocity at the start is 5.5. That's 5.5 squared. 4.6 squared divided by 5.5 squared. So you get 0.995, 0.6995. Rounded to two significant figures will just be 0.70. Rounding to two significant figures means rounding to this figure here. Rounding to this figure here will give us this. The ramp Q is removed. So they remove this ramp. The car leaves P as in B and now lands directly on the ground. So, okay. So at time T equals 0, it leaves P and it hits the ground at T. So here at the end on the figure, sketch the variation of time T for the vertical component of the car's velocity. So it leaves the ramp, now it's got no other ramp to land on, but it just drops straight to the ground. Okay, so well that means that at the start it has a positive, it says you shouldn't care about the actual values, but it has some positive, say, I don't know, here, some positive vertical component at the start, and then it is deaccelerating to its max height at some time. Terrible drawing, but whatever. Okay, but then its vertical component is now not acting up, but is acting down as it passes that max point, right? The max height. So it's now going down, but it was still deaccelerating at the same rate. It would just be accelerating its velocity in the opposite direction. So it's just going to continue through here. The same, this line is supposed to be the same. Right, that's, apology for the drawing, this is supposed to be a straight line. So it's constant, the gradient is constant. However, at the end here, this value should be lower than this value here. I mean, in terms of its magnitude. You know, this is V1, this is V2. The absolute value, so whatever this is, needs to be bigger, right? Because it's dropped past the ramp. It starts higher up, and so it's going to have more time to accelerate to the ground. Right? We have a ramp, it drops here. The velocity here of this car is going to be greater than the vertical component of the velocity is going to be greater than the velocity here. Right? Because it's spent more time in the air, so it's going to accelerate for longer. Okay, so that would be your answer. Obviously, you draw it better than me. Okay, question 2. So we have a VT graph. The ball moves in a straight line from point P at t equals 0. The mass of the ball is this, which is 0.4 kilograms. Use this figure to describe without calculation the velocity of the ball. So what's happening? So from 0 to 5, its velocity is decreasing at a constant rate, right? So velocity, not decreasing, did I say decreasing? Increasing. Increasing at a constant rate. Velocity is increasing at a constant rate to t equals 5 seconds. It then starts to decrease, right? Starts to decrease its velocity all the way to 0. It then decrease, I guess we're like this. And velocity is decreasing at a constant rate to velocity of 0 meters per second, right? But at t equals 10 seconds. So it increases to 5 meters per second, and then it decreases to 0 meters per second at t equals 10 seconds. It then continues to decrease, or it continues to de-accelerate. Now it's accelerating in the opposite direction. So it then, you say the velocity increases at a constant rate, but in the, man, my writing is awful today, opposite direction. Velocity is increasing at a constant rate, but in the opposite direction. And this constant rate will be the same as the decreasing constant rate. The decreasing rate. Right, it's the same gradient. So if you think about it in a line, it would be, okay, so it starts at 0, then starts to accelerate or increase its velocity at a constant rate to a point at 8 seconds. It then starts to zoom, and then starts to slow down, starts to decrease to 0 at 0 meters per second velocity at 10 seconds, and then it starts to move in the opposite direction. But it's de-accelerating from 8 to 16 seconds at the same rate, because it's de-accelerating. Well, when it gets to 0, it's still de-accelerating, but it's just now going to move it in the opposite direction. So it's going boom, slows down, 0, and then boom, back the other way. Use the figure to calculate for the ball. Okay, so t equals 10 seconds. The displacement at t equals 10 seconds. Well, the displacement is just going to be s equals to the area under the graph. The area is all of this. T equals 10 seconds, right? So what is that area? Well, it's going to be this triangle plus this triangle. Well, it's going to be half base, which is 8, times height, which is 5. Half base, which is 8, times 5, plus half base, which is in this case 2, and height is 5. So 2 times 5. Well, that's going to be what? 4 times 5 is 20, plus 5. It's going to be 25 meters. It's 25. The acceleration at t equals 10 seconds. The acceleration is just going to be the gradient. So the acceleration at t equals 10 is just the gradient of this line, right? Or the change in velocity over time. Also, you just pick 2 points because the gradient's the same. So let's pick these 2 points. So the acceleration will be v minus u over t, which is the gradient. At the final velocity, let's say, take this as the initial, 5 meters per second, and this is the final, 0 meters per second. So it'd be the final is 0 minus initial divided by the time taken from those two, which is just 2 seconds. So this is just minus 5 over 2, which is minus 2.5 meters per second squared. Maximum kinetic energy. Well, where does the maximum kinetic energy occur? Well, EK is a half mv squared. Where is this v squared maximum? Well, it's not here. 5 squared is 25. It's here at minus 15. Because minus 15 is squared is going to be a positive number, which is going to be bigger than this. So set this here. And because its velocity is the greatest here, its speed is the greatest. It's just acting in an opposite direction. I feel like the thing that trips people up is the directional component of these questions. Negative just means it's acting in opposite direction. That's it. Of whatever direction you're picking. So max EK is just going to be half times the mass, which was 0.4, right, which they gave to us, times minus 15 squared, which equals minus 15 squared times 0.4 divided by 2, 45. 45 joules. Finally, use your answer. Determine from BI, so these two, determine the time it takes for the ball to return to P. As I said before, it's accelerating. It's accelerating here, then begins to deaccelerate, and then at this point it turns around and goes back in the opposite direction. We're given that it moves displaced 25 meters in the first 10 seconds, right? So at here, and as it starts to turn around, it's moved 25 meters. So if we look at this, this is 25 meters, and this is where the ball starts to move in the opposite direction. So its initial speed here will be 0 meters per second, but this ball or object, whatever it is now moving in the opposite direction. So we simply find the time it takes to get back to P here, right? We have its acceleration as well. Its acceleration. Now we're treating this direction as positive. So its acceleration is 2.5 meters per second squared. You could keep it as negative, but that means you have to treat this as negative. So this would be negative, and this would be negative. You still get the same answer, right? I'm just treating them as both positive because they're both in the same direction. I'm talking about displacement in this direction and acceleration in this direction. So I can find a time it takes from get to here to here. Right, so, S equals 25, A equals 2.5 meters per second squared, meters. We want to find the time, and we have our initial speed, which is 0 meters per second. So from these, what equation can we use? Well, we have this one. For U, this is 0, so this will just go away. And this will become, 25 equals 2, that's 0. Right, because U is 0. Half 2.5 T squared, which we don't know, which we want to find. Therefore, we get T squared equals 2. 2.5 divided by 2. 5 divided by answer. Square root. This is rounded to two significant figures. You rearrange this, you get a T equal to 4.5 seconds. Two significant figures. However, that's the time it takes to get back, right? The time it takes to get there is it's asking for from T equals 0 to return to P. Just going this way and then coming back. So to get to that point, it took 10 seconds, and then to get back to P, it took 4.5 seconds. So the total time will be 10 plus 4.5, which is 14.5 seconds. I feel like this video is getting too long, but I will do this final question. Might have to go a little faster. Gotta keep you guys engaged. Okay, a man is standing and he throws a ball vertically upwards 5.6 meters per second. So, they're changing this scenario, but this is still a projectile and we'll still use everything the same. And you'll see on the worksheets, same. The ball leaves in his hand from some height, blah, blah, blah. Show that the ball reaches a maximum height of 4.7 meters. Well, he's throwing this ball at an initial velocity of 5.6 meters per second. At its maximum height, its final velocity will be 0 meters per second, right? It's not moving, it stopped. As its maximum height, because then it's going to drop back down. We're accelerating, we have an acceleration, because we're treating it as up here. Our velocity is up, it's minus 9.81 meters per second squared. Okay, so now we want to find what is the displacement, what is this distance here? Apology for the bad drawing. Okay, what is this distance? Well, we have this equation. We have this, we have this, we have this, we want this. B squared is 0 squared equals to U squared is 5.6 squared plus 2 times minus 9.81 times S, which will give us this distance from here to its highest point. Therefore, if we rearrange this, we'll get S equals 2. Guess I'll do it for you. Okay, if we rearrange this, yeah, 2 times 9.81, 9.81. So you take this over, you get 19.62 s equals 5.6 squared s. So therefore we divide through by this 0.62, get s. So therefore s equals 2, 5.6 squared divided by 19.62. So this is 1.598. Rounded will be 1.6. So well, that's not that, but we're only calculating from here to here. We also have this point. So h max will equal to 1.6 plus where he throws it from the ground, plus 3.1, which is 4.7 meters. Okay, there you go. The man does not catch the ball as it falls. Calculate the time taken for the ball to fall from its maximum height to the ground. Well, it's at the top. Its initial speed is 0 meters per second at the top. Drops down, height of 4.7, which we found before, so that's its displacement. And its acceleration, now, we can treat it, if we want to treat this as positive, if we're treating it acting down, well, its acceleration, we can just say it's 9.81. Positive now. Acting the same direction as the displacement. And so if we want to find the t, well, we can just use this. S equals ut plus a half a t squared. We have this, we have this, we have this. We can find the time. Right, so I'm treating this as positive and this as positive, both acting in the same direction. You put them both as negative if you want to make the direction positive. It's going to give you the same answer. So you get 4.7 equals 0 plus a 0 half 9.81 t squared. Therefore t squared will give us 4.7 times 2 divided by 9.81 is 0.985 ... So t will just be the square root of this. Rounded, that would be 0.98 seconds. It really frustrates me that they don't give you enough space. I mean, what are we doing here? You're trying to save on space? Just give them more space. Give the students some working out space, man. The ball leaves the man's hand. So this is the same concept of what we did in like the first question. So basically we want, how's the velocity changing from his hand at t equals 0 to the ground at t equals t, big T. We're not interested in numerical values, so we're just getting an idea. Well, he throws it at some speed, which is positive. Okay, so we have some positive value. It then deaccelerates to rest at some time, right? Let's say here. Deaccelerates to rest at the top, right? So he throws it at some speed, deaccelerates to rest at the top. It then starts to drop down, but it's accelerating at the same rate that it deaccelerated up. The acceleration due to gravity is going to be the same the whole time. So it goes up and deaccelerating at the top, and then it starts to accelerate, but in the opposite direction. The velocity will be increasing in the opposite direction. So it'll be negative velocities, but it's doing the same. However, it's dropping then past him and hitting the ground. So this bottom value has to be greater than its initial velocity. So again, it's just a straight line. Fully drawn straight line, but this value here, let's say this is -10, it's not, and this is, I don't know what it was, 5. This has to be, this value, the 10, has to be greater than the 5, right? Because it drops down further than where when it starts. So have more time to accelerate and increase its velocity in the opposite direction. That's it. It's 3 marks. It would be to do with keeping it the same gradient, this being smaller than this, and ensuring that this is on the negative. State what is represented by the gradient. The gradient is just the acceleration, change of velocity over time. The man throws the ball, second ball, same velocity, same height as first ball. The mass of the second ball is greater than the first ball. Assume negligible air resistance. Okay, so we have same thing happening, but just with a larger mass. So how do the first and second ball compare to the magnitude of their accelerations? Well, these would be the same. We have the same acceleration because it's changing the resultant force, but it's not changing the acceleration, because no matter what the mass, it's still being affected by the acceleration due to gravity, which is 9.81 meters per second squared. So no matter what mass, so in hypothetically, I mean, if you had like a feather and a steel ball, if there was no air resistance, obviously there will be a great air resistance on the feather. If there was no air resistance, if it was in a vacuum, if you drop the feather and the ball, well, they would land at the floor at the same time. Pretty weird, shouldn't make sense, but it does. It would happen. And so the speeds that they hit the ground, well, these will also be the same. They're accelerating at the same rate, well, the speeds will change. Same, right? Accelerations change the velocity over time. Same, baby. Okay, that's it. I feel like that was a little too long, but look, I went through a bunch of questions. Hopefully it's useful for me to go through a bunch of questions. I tried to explain as much as possible. But that's it. And now we're going to go into the philosophy of motion itself. What is motion? Are you ready? Are you ready for me to discuss probably one of the most mysterious and interesting phenomenon ever found by man? Motion. What is motion? What is it? What is it actually? Everything is in motion. Everything. Right now, sitting here, you are moving at unfathomable speeds. Chaotic motion. It might seem like things are still around you, but it's not. If you take another perspective, another frame, if you're sitting in a car, things in the car are still, but someone looking outside the car, well, the whole car is moving. Same situation for what's happening to you right now. The Earth is rotating, it's orbiting the sun is orbiting the solar system's orbiting the whatever, the solar system's orbiting the galaxy, it's crazy motion happening physically right now to you and me. And if we were to gain just 1% of a perspective on our current situation in regards to the physical motion that we're experiencing, it would disintegrate all of the bullshit, all of the problems that we're having collectively and individually. It will completely recontextualize your life and bring what's important to the forefront of your living, of what you're doing. And that's really one of the powers in physics and philosophy and doing these contemplations. It really cuts away all the shit, all the distractions, all the bullshit that we're worried about, that we're interested in, and it gets to the point of what is happening and how crazy it is. And that's really the benefit of contemplating here, and one of the big benefits of physics itself. However, if we want to go even further into this idea of motion, true motion is emotion. This is the emotion that you feel. This is what really sets in motion so many things for humanity. The congruence you feel with nature, this feeling that you get, this wonder that you feel when you look at nature and observe nature. This is true emotion. True motion. It's the stuff that drives humanity forward, makes us discover more. It gives us energy and momentum, and it moves us. The great works of the love of Gandhi, or the contemplation of Socrates, or the psychological depth of Jung, the creative rationale of Einstein. These great works have moved humanity. We stand on the shoulders of giants. We stand on that past motion set by these incredible human beings who were deeply congruent and in touch with nature. And it was from this place, this emotion that they felt, which pushed forward humanity so much. And that is true motion. It's the emotion you feel towards nature in your experience and your existence. This is real motion. Yeah, motion is a very, very interesting thing. It's not simple at all. And gaining perspective on it will give you perspective on everything, because everything is moving, including you, physically, psychologically, emotionally. So yeah, that's it. Like, subscribe, and I'll see you later.